tell us about adaptive estimation of the rank of the regression coefficient matrix. I'm not sure what that is, but hopefully they'll learn.
Thank you. I would like to thank the organizers for inviting me. So it's joint work with Jinbing, and you can read about it. It's currently under revision on arXiv. And so let me first, I'll give first an introduction, explain the model, tell you what the model is, give a new procedure, give the properties of that procedure, and then everything is fine, of course, good results, otherwise I wouldn't present them, but we can do better. So the cool thing of this whole approach is that there's a tuning parameter, inevitably, but we're going to adaptively estimate it by an iterative procedure. So we get the optimal tuning parameter, and if time permits, I will say a little bit about extensions. So I just consider a regression model. I observe x and y, and all those letters, including the a and the e, they're all matrices of commensurate dimensions. So we observe x, it's an n by p matrix, and the rank is q. And again, x is known. A is unknown, that's the basis of regression coefficients. It has a rank r, and r is also unknown. And the entire focus of this talk, this paper, is to estimate r. Not to estimate the mean, xa, no, to estimate r. And we assume that E has, that's the error matrix, say, and has independent, or ID entries, in fact, mean 0, variance sigma squared. And so the number of parameters, you can, of course, if the, okay, is the pointer? Yeah, there we go. If the rank is q, which is less than p, then you can write x as an x tilde and n by q matrix. So essentially you have q by m parameters to estimate. And my sample size, I have a sample size for y is n, but each vector, each entry is an n-dimensional vector. So in fact I have nm observations. But still qm can be too large to say anything meaningful. So what you have to do is to impose sparsity. You can do sparsity that the entire matrix of A is sparse, or you have rows that are totally 0, which would correspond to columns of X that don't matter, right? So that would be variable selection. And so in this setting here, you can go back to work, and there are many others, of course, but in this particular setting, this is limited, still limited list of references. So we're not going to do sparsity in this sense. We do something more interesting, perhaps. It's reduced rank. So I assume that A has a structure, namely it has reduced rank. And so A is a product then, right, of an A1, which is a P by R matrix, and then A2 is an R by M matrix. So I have just fewer linear combinations that explain the variation of Y. So for fixed dimensions, M and P, lots of this work, of course, goes back to Anderson. So this is just the first reference, but there are many more references. There's also Eisenman, Robinson, Rao, and there are many others, and it's all very nicely told in the story, in the book by Ransom and Ballou in '98. In the high-dimensional cases, fewer work about this kind of stuff. Some joint work with Flory and Yuan. There's work by Christophe Giraud. And then the last two references, they consider a more general setting, but they use a nuclear norm type penalty, which is suboptimal in this case. So most of my interest was improving upon this paper here. So a classical approach here so the estimation of the rank, so in fact I should say here the testing of the rank, if the dimensions again are fixed, then you can just work out, it's very tedious in all this work, but I mean there is a likelihood ratio test which goes back to 38 by Bartlett. improved by Xu and Anderson again. But again, that's for fixed dimensions. And so what we want to do, we don't want to do testing, in fact, we want to do estimation. And we would like to get a non-asymptotic bound that's adaptive, that's easy to compute, all that, and that's consistent. So again, I was inspired by this work, and it was simply minimize the squared Frobenius norm plus mu times the rank. There is a choice in that paper that says that take it as a constant multiplied by the square root of those dimensions here times sigma squared, and take for the constant 1 or 2 or something like that. And that's all very nice because there's a closed form for the minimizer here that you find for the rank. And if you want consistency, then you make an appropriate signal assumption and you get it. So great. So what can we do better than this? Well, there's a disadvantage because you need to know sigma squared. And you also need to know C. And you can, of course, do cross-validation, but then you would find the best fit, which is not necessarily the optimal rank, the true rank. There's another problem. I mean, I don't know sigma squared, well, big deal. I mean, you can estimate it. This would be a good estimate, a good candidate. Of course, I don't want to divide by 0, right? And so what you can do, well, what can you do if nm is equal to qm, or it's almost 1 or 2? Then you have a problem with this method. So can we do something else? Well, use another criterion. So it's kind of a generalized generalized AIC type criterion that we'll introduce. So there's work by Giraud, as I mentioned. He uses indeed a different estimation scheme. Does not need the value for the parameter sigma squared. He doesn't need it at all. In the paper, you can find lots of simulations, or not, a few simulations in a low dimensional setting where it fails in the sense that that estimator here is not consistent. I should not be worried about that because he doesn't claim to estimate the rank. He wants to find, he's interested in an oracle inequality for the fit. So it's just a method geared to something else. But it may actually work that it would estimate the correct rank, but it doesn't, unfortunately. So we have to do something else. The other procedures I'll show later, they are very sensitive to the choice of that constant, which is perhaps not a constant, which I'll come back later. So let me go to the criterion. I call it sigma hat squared k, and k is the index. And, sorry. So essentially here, it's the best fit. So y minus py k squared, our Greek friend Pythagoras will tell you that this is equal to this. And so this is the best fit in Frobenius norm by a result by Schmidt or Eckert Young. It's closest in Frobenius norm to this quantity here of elements of the form in the range space of X. So of the form XB, where the rank is at most K. So this would be the best candidate. What is PYK? It's just a truncated SVD. So the GJs always stand for the singular values, and I've ordered them from large to small, as usual. So the PYK is simply the truncated. So, and that's essentially what we do. So it is fairly easy to compute. Well, easy to compute, you have to compute the SVD, I agree. But if you have done that, then sigma hat squared k is very easy to compute. And so I don't want to divide by 0, of course, nobody does. And so there is a range restriction here for my k. There's a natural restriction. K must be the minimum between q and m, of course. But also, if there is a restriction that I don't want to divide by 0, and that is a serious defect of this method. So there's no free lunch. This is the main defect of this method. Otherwise, it's all great. Now, what's the role of the lambda tuning parameter that I want to estimate later? It should be large enough so that I don't, so large lambda will give me a small rank, and vice versa, a small lambda will give me a larger rank. And I want to find kind of the optimal one. So let me go back to the criterion. It's decreasing, the numerator and denominator are both decreasing in k. So in the entire work, I think it's 80% is our very interesting monotonicity properties. And you can prove this theorem simply by monotonicity properties. So your criterion is essentially, the theorem tells you that it is indeed, first it's decreasing and then it's increasing, has a unique minimum, and the minimum is characterized by this. The number of singular values of py that exceeds a threshold, which is variable. In fact, this is your criterion back. So you know exactly for a given lambda what you get, right? And again, this result is simply proven by a whole series of monotonicity arguments, which will be pervasive in the rest of the work as well. So I find it fascinating because the previous work was minimizing essentially this criterion, was minimizing this criterion here, which is equivalent by minimizing this criterion. And there you also have a unique minimizer, and the minimizer is given by this, the number of singular values of py that exceeds a fixed threshold. So in the picture, you would essentially see this. I plot here in red the singular values of py. You kind of have here an elbow, but you know which point should you choose. I choose here a very nice situation. I chose here a low-dimensional case, so everything should be fine. I kind of know what should be the optimal tuning parameter here in this case, right? So I cheat, and so this would be my perfect fixed threshold, and the green one is the variable threshold. And the minimum of this green line should also give me my choice, and it's indeed it is above. So the red ones are above the green ones here, and here's more or less the same. You can't quite see the difference. And it's also the fact that it gives you the minimum of the green line. So that's the theorem essentially, and the fixed criterion gives essentially the same result, same minimizer. So this is what's going on. So it's just fixed threshold versus variable threshold. So I consider two cases. The first case, because typically if you want to have consistency, you want to have a signal condition. I'll start with a case where you don't have any signal, so you don't have any signal condition because the signal is 0. So we will need all the time sigma hat squared. That's the toy estimator because we don't observe E, of course. So, but this is close to sigma squared. So, indeed, if you don't have any signal, then if you choose your lambda large enough, larger than the largest singular value largest singular value of PE divided by sigma squared, so that's the singular value of a matrix of certain dimensions with IID observations, then you get the right answer. So if you want to put this in, so this is still a random object, so if I don't want lambda to make a random object, I have to say something about D1. D1 is highly concentrated around the mean. There's essentially Borel's inequality. I have a very sharp bound for the expectation of the singular values, and this is, in fact, this here is true for any singular value, dj. Thanks to Ian, we have that sigma hat squared, our toy estimator for sigma squared, is very close to sigma squared. if I assume normality, and so you have, then you get essentially, if you put all those things together, what you get is take lambda larger than this quantity here, does not depend on sigma squared, right? I get my correct answer. And that's exponentially fast, exponentially in nm and m plus q. So again, now we are going to consider the case where xa is not 0, so we do have a signal. And again, the drawback of this I shouldn't emphasize too much, but that's the only drawback, I should say, of this method, is that your range is limited. But furthermore, it's restricted by lambda. So if I see here, I would like to take lambda as small as possible. Previously, so I want to take lambda as large as possible, large enough so that I kill the noise. So a trivial remark, but if my true rank is outside the range over which I minimize, then I always have that whatever I find is less than the true rank with probability 1. That's a trivial observation, but that's important. So now suppose that your true rank is within the range. If lambda satisfies equation 5, so it has to do with the noise, so the d1 squared p of e, that's my measure for my noise in this case, is larger than this criterion. This kind of sigma squared, but not quite. And it's ugly because it depends on lambda and on r. But if this is the case, then I have k hat is less or equal than r. And this is crucial. If I have a singular value that has enough signal strength, so if I make here an inequality, then this is essentially twice this term here, right? Then I have a lower bound for the rank that I found, k hat, say. It's between s and r. And if this condition then holds for s is equal to r, then I have my consistency. So is this a good result? Well, yeah, I think so. What we did, we generated many x's and many a's, and then we choose the largest lambda, which gives us rank consistency. And then I compute, oops, sorry, not too fast. Then I compute this quantity here, square root of lambda times sigma hat r. And I plot that against my signal. And it's exactly a straight line. And my claim, I didn't prove it, but I think if I plot the signal, drxa, against this kind of confidence band, it's right in between. So it simply tells you we're looking at the right quantity, which in some sense that's nice to know, but on the other hand it's bad because that quantity, that depends on my lambda, my tuning parameter, and on r. And I don't know r, I try to find r. So how can we solve that? Well, by the following lemma. So again, assume that we are in the allowable range, which depends on lambda. And now on the event that with a 2 here, twice d1 squared, twice my noise is bounded by lambda times sigma hat squared, then I have that sigma hat r squared, the quantity that I'm interested in, is centered between sigma hat squared and something larger than sigma hat squared. And so this depends on lambda if this upper bound is loose or not. So what I'll do, I'll prove this claim. It's just 2 slides. And the reason that I prove the claim, it's not because I think this is so important, but I'll show you an iterative algorithm later on, and all of a sudden you get a quantity that comes out of the blue. But if you have seen a proof, it doesn't come out of the blue completely. So again, it's a very simple proof, especially for the upper bound. This I just did here. This is just our friend Pythagoras. Then this truncated SVD lies in the range space of X. So this is the approximation result by Schmidt, or sometimes referred to Eckert-Young, but they were in the 30s, and Schmidt was in 1907, so it's a little bit earlier. And then you can combine those again due to Pythagoras, right? And then you rewrite it. And so you get this quantity here. Now for the lower bound, and that's what we really need, you start again with Pythagoras, so this is the same line, then the squared Frobenius norm or Hilbert-Schmidt norm is nothing else than the sum of the square singular values, right? So this would be the tail of those values. Then I get rid of, here the mean disappears. Here I use while. You stay in the 1910s. And then we can combine it again, and we get this quantity here. And my question would be, is this monotone? So forget about this minimum here. Let's, I mean, that's a technical detail, right? And I only claim that sketches the proof. And so I call ek squared is essentially that quantity here. And so E naught squared is sigma hat squared. And it's a decreasing sequence, or an increasing sequence. And so you get indeed that monotonicity property here that's equivalent after some tedious manipulations, but it's just equivalent with this. And that holds, that's equivalent with lambda larger than this quantity here. Now you take k is equal to 0, you get here simply E squared, so E squared over nm is your sigma hat squared. And you get here d1 squared plus d2 squared, well that's about 2 d1 squared. And you get here 0. And so if I go back, that is exactly your condition 7 here. And then you get all the stuff going on because this is indeed monotone, and this will be larger or equal than E naught squared, which is our sigma hat squared, and we'll also claim. But the only reason is, I just point out again this condition here. You'll see that later. Which looks, if I just introduce it like that, looks very odd. Okay, so now the corollary here is that if I assume indeed that previous condition, and I assume enough signal, then I get my claim that my estimators between S and R, where S, I have the signal condition on S. So if I take S equal to R here, then I get my consistency. So if lambda is large enough to kill the noise, and small enough so that I have enough signal, I'm in good shape. That's essentially what it's saying. So we got this quantity here. If I want to have it less than 1 plus delta, that turns out assuming simply that R is less than this quantity here. So it's nm over lambda, that was as before, times a little bit less. If you assume that, you get this, and then everything can be put in a very clean form. So take lambda larger than 2 times square root of m plus square root of q squared. So there's no sigma squared here, right? Assume normality. Assume that R is essentially small enough, so you truly have low rank. And assume that you have enough signal, like this here. Then you get your consistency. Again, consistency when you take S is equal to R. So, but this is what's going on. And so that holds exponentially fast in mn and m plus q. So no log over log stuff. It's really fast. You can see that in simulations. So this is all very nice. However, the choice of lambda impacts, of course, the values that I can consider. If R is my true rank is outside the possible range, then I cannot make any claims except the obvious claim, the trivial claim, that whatever I found is less than the truth, which is still meaningful in some sense, just gives you a lower bound. But if you're within the true range, then you can make consistent guarantees, and they go very fast under a suitable condition on the singular value, the R singular value of xa. Now the interesting thing is to note is that condition on the singular value that becomes milder when lambda it scales with square root of lambda. It becomes milder when lambda becomes milder. So what you want is lambda large enough, but not too large, because if you take too large, then your signal may be too weak. Your signal condition, I should say. So that comes to the innovative part, I think, of this whole work, is that we try to find the optimal lambda. So we start with a pretty good choice that guarantees us that whatever we selected is less than the truth. And that's not so hard to do. Now, with that particular choice of k hat that we find, we would like to find a new lambda. And that would give us a new lambda. I'm going to tell you in a second how, or maybe 2 seconds. And then you would like to find, plug in that lambda in your criterion and minimize the criterion and find a new k, and so on. And would something like that work? Well, the answer is probably yes, because otherwise I wouldn't be here, but that's the idea. So we start with, well, let me first give some notation. So essentially what I need in that whole procedure are essentially values of squared, the expectation, say, of squared values of a Gaussian matrix of the right dimensions. The rest is kind of, and here my k hat, t is for the step size. This is simply the allowable range. So if my lambda gets smaller as t increases, I hope, then my allowable range will get larger. We do have formulas for SJ. I should say you can prove upper bounds and lower bounds using interlacing inequalities, but they are upper bounds and lower bounds, and depending on the size of the dimensions, they are good enough or not. So I just advise you to just use Monte Carlo simulation for this. That's what we did in the simulation. That works perfectly. But you can get beautiful formulas if you want, and it looks much more impressive, but this is really what you need. You just use your computer. So the starting values is essentially the previous criterion. Just use, because S1 is essentially square root of n plus square root of q squared, and I multiplied by 2, a factor 2. Maybe I should multiply by 2 plus 1 plus epsilon, but you know, I leave out as many details as possible, so this is slightly larger than 2. Anyway, and then minimize simply our criterion. And the range here depends on the first choice here, right? So those are the starting values. Now what are we going to do? Now we're going to update our lambda. So if we find k is 0, then we're done. If it's larger or equal than 1, then we are going to update. How is the update? Well, this guy here should remind you of the lambda that I showed you in the proof. It is not exactly the same, but it is similar. It has a similar flavor, and it is just used to get monotonicity properties working and to make sure that the sequence of lambdas is indeed decreasing and that the k's are increasing. But always the k's here are always less or equal than r. So that's not trivial to get, and so that's why perhaps this looks so weird. But that's the main idea. So you get a precise form for your update. You plug in that update in your criterion, that's your new lambda, and you simply minimize that lambda. And so the procedure is free of sigma squared. Those weird quantities r and u, they can be evaluated by Monte Carlo, essentially. That's not a problem. Computationally, the method is not expensive. Well, it is expensive. You have to compute a single value computation, but you only do that once. But if the dimensions are large, I'm not saying that it's not not complicated, but that's the only thing that you need to do. And to find a new rank, in this step here, normally you would start with 1 or 0, but since you have an increasing property of the case that we will show in a second, you can just start with the previous one and continue. So it is really not a lot of computation. So since this is about scalability, I think it's a very good algorithm. And you repeat till it stops. So the most number of steps that you can have is r. That would be the worst case. In some sense, it would also be the best case because it would give you the least signal. I'll get to that in a second. But you know, the number of steps is just finite. It's just at most r. Okay, so this lemma is the crux of the whole why it is so good. And again, it's proven by monotonicity arguments, and they seem to contradict sometimes each other because it looks all weird, but I'm convinced it's all correct, and because the method just works like a dream. It works really well. I'll show you some simulation in a second. So you get a decreasing property of the lambdas, which gives you immediately an increasing property of the case. That's not a problem. But the guarantee here is not trivial, that you always will select something that's less or equal than R. Because you get closer and closer and closer to R. And again, that's with probabilities in the normal regime. If I have normal errors, I get simply exponentially fast rates. The probabilities tend to 1 exponentially fast. E to the minus m plus q, q plus m, and e to the minus plus e to the minus nm with some constants. So it's really fast. So compared to the previous method, I can say that this is better. I mean, it gives you something closer, at least, to the truth. What's good, I showed you that the lambdas are decreasing, right? So that is good because my range gets larger and my signal condition gets weaker. And so the proof is very specific. I mean, you will really want to maintain this property, that k hat is less than R at every step. And so what you would expect indeed is that if you have a certain signal to noise condition, then you get consistency. And hopefully that is a weaker condition, of course, than the first algorithm. So one way of formulating that would be, I have a sequence in mind from 1 to R, a subsequence here of length, say, t, or t plus 1. I use my initial value as before. That's not random, right? And then I use lambda t as in 13 as before, but I use those case and not the random case, if you know what I mean. So just the case kt's of this particular sequence. And I assume that my r and delta, that my r is say small enough, my delta is large enough, such that I have this criterion here for the first one, and that my signal condition here becomes weaker and weaker because my lambda becomes smaller and smaller and smaller. And if this is the case, then the algorithm finds the truth with probability 1, 10 to 1, exponentially fast. So this, in some sense, guarantees, I mean, that you find the optimal tuning parameter. So the ideal case would be you're done in one step, computationally. But if it takes R steps to recover the true rank, then of course this condition here for R becomes the mildest condition possible because your lambda is the smallest possible. So let's see how that works. So first of all, we use BSW is Marten Wegkamp so that is the fixed threshold, sigma squared times a constant, and then the values of the constant are mentioned here. Okay, so what do you see? We are yellow, and here's the signal to noise condition, and here I have matrices that I generate in a special way of increasing rank. So we do perfect till the signal to noise condition becomes smaller than 1. The other methods, if I take a small, like in the red one here, a small constant, I'm overfitting here, and then kind of underfitting there. So it seems to be a little bit better here, but it's just not stable because it depends on the value of the rank. We have a couple of high dimensional setting, low dimensional setting, you get the same pictures. If you do the other way around, if you take, say, for instance, the purple line here, it's more or less, it's okay here, but it gets really bad here. It's the other way around. And we're just fine with the theory if you have enough, if you give me enough signal then you get the right quantity here. And of course here m is equal to 30, so if I'm interested in low rank, and q is equal to 20, so if I'm interested in low rank, to have ranks that is about 10 at most is not so strange. So this is in a high dimensional setting, but essentially it's the same picture. Now the case where n is equal to q or close to q, so if n is equal to q, then you cannot estimate sigma squared anymore. And so the result in 2011 doesn't hold. I mean, I don't have an estimator for sigma squared, so I don't know how to run that algorithm. So what do we see here? It's actually, well, if you plug in the values, for q is 143, so the correct q is 150. Sorry, 143 or 149. So it is very close to n. So for 143, you see that we do fine, but we have this drop here, and it's essentially, this is a natural constraint for R, of course, 30. So if you want to have low rank, essentially what you get is something like 11 and 13 here. And so I think that is low rank in this case, but you can see that this is just the artifact, what I said before, of this method. I mean, you really should be looking for low rank. Now, so 30 compared to 13 compared to 30 is not so bad. But you see that it does perfectly well, and then it just drops, it doesn't. Whereas the other methods do something, and it gets worse and worse, of course, if you get this. Of course, I can show different pictures where this is much longer the case, but I also want to show you the artifact of the method. But the other methods, they are kind of wobbling because the estimate for sigma squared is just not very good. And you still don't know if you should choose 0.7 or 1.3. If n is equal to q, sorry, then I have nothing to compare with. And then you can see if you increase m, then you get a large and larger range for your ranks. So this is all in agreement with the theory. So what I said is that the possible allowable range of ranks of which you minimize, that increases, which is good, of course, as lambda decreases. And so so suppose that for the first lambda was just too large, so that the true rank lay outside. It is possible that you run this algorithm a few times, and then your allowable range actually covers the true rank. And that's indeed the case. So I'll show you. You can prove some theorems. You have some theorems for that, but the picture's, I think, much easier. So in a low-dimensional setting and on a high-dimensional setting, what you see here, the first GRS is the first method, the generalized rank criterion, and it just drops here because it's out of the allowable range. The allowable range here is, I believe, 7 or 8, something like that. And then, you know, it will just choose 7 or 8, whatever it was, all the time, and it's just done. Whereas the other method will continue doing that, and it just stops doing that when the signal-to-noise ratio is not good enough. And in the high-dimensional setting, you have the same situation. There is no difference. Now, this is not I'm not a very good salesman. Of course, I should show you a picture like this. I just give me plenty of signal, and the original range is 7, so the first algorithm just stops there and can't do better, whereas the other one will just, I have enough signal strength, and so I will find the true rank all the time. And it's just perfect here. So it's always a matter of if you have enough signal strength, but if you have enough signal strength, then this is a really good method. The only deficit is simply that there is a limit on the range. But if you give me enough signal, you will just, if that's reasonable, you will always find it. So maybe I should have showed you pictures just of this, and then you thought, wow, this is a very good method. But of course, you can have this situation too. So there's not always a free lunch, but it's a very stable method. So I have 5 more minutes to talk about a little bit about extensions. So most of those things, as I said, they're just proven by monotonicity arguments, the whole paper. And sometimes I rely on random matrix theory, just concentration inequality and that kind of stuff. And so the Gaussianity comes in here, that I'm always looking at P of E, not E, but P of E, which has, this is a smaller number than D1 of E. Now, you can, I write out for P the eigen decomposition, then by the symmetry here, you get simply this singular value is the same as this singular value. Now, U is this just a rotation of E, right? So this is again Gaussian then. And then this lambda, this just, since the projection matrix, it's either, it has ones, they're essentially zeros, and they have a bunch of ones, and then they have a bunch of zeros. So this just knocks down the dimension, essentially, of this whole thing. So essentially, you get a smaller Gaussian matrix here, right? Perfect. So then you can just rely on Gaussian matrix results. And then you get very sharp results, believe me. If that's not the case, then if you don't have Gaussianity, then I don't have that the transformation or this transformation is Gaussian anymore. In fact, if this is just independent, this is no longer independent, but the rows remain independent. So Verschienen has lots of results, and he has this interesting result. If I just have that E is independent, sub-Gaussian, and then you get this result. So if I simply assume that this is the leading term, Q is little o of n, then this is essentially square root of n, and then everything goes through. So that's an important case, and I will show some other cases where you can get away with 4 moments only. So my conjecture, and I've not proven it yet, is that, so this will be used in the simulations, or squared I should say, and I think it's really close to this, even if the errors are not normal. Why do I think that? Here. So I use my normal matrix C, and I have here my independent t-distributions of various degrees of freedom. So this one will have 4 moments, and this will have 11 moments. And essentially it's a straight line for this ratio. It's not quite strange, and if you straight, and if you would zoom in, you would see actually a little bit of this, but it's just a little bit, right? I mean, it's essentially a straight line. You see a little dip here and a little dip there, so I'm very curious, but I didn't have time to investigate it further. But this definitely claims that we can simply use our algorithm even for non-Gaussian errors. If you do that, you get the similar situation. It works great. So that's for the heavy tails. There are some theorems that we have as well for the heavy tails. So the first algorithm simply works if in a high dimensional case. So if n over cube tends to 1. So q is the rank of x, so that's bounded by p and n. So if p is really large, then q is probably very close to n. So the high dimensional case, p is very, very large. Q is kind of n, so that's this situation. If that's the case, you have 4 moments, then you can prove this. The first algorithm works under the same condition. Otherwise, if you want to prove more, for the second algorithm that gets much harder, then I can only consider skinny matrices for the mean. So XA is either this or it's really this. If that's the case, then we can more or less simplify the procedure a little bit. And this looks much friendlier now. But it's essentially the same procedure. And under the same conditions, plus the skinniness of the mean matrix, you get more or less the same result. So the sequential procedure works. Now, I'm not saying that's exponentially fast anymore because it isn't. So the convergence rate here is much slower to 1. But That's the price that you have to pay if you don't have, if you have only 4 moments. It's just 4 moments that you have here. And so it's an open question if I don't have this condition here and this condition. To be honest, I don't know. So before you ask, I mean, I give you the answer right there. That's still an open question. But otherwise, this is actually one of the few procedures that you can actually fine-tune your tuning parameter. You start with a good one, and then you get a better and better and better one, and it stops after a finite number of steps. You can apply that to the special model, where you just have a mean and error, right? Same thing. And so here are the conclusions, but I think I'm running out of time. So essentially, we have a very stable procedure as long as R is in the allowable range. And essentially, I should say about that is that it fails when nm is small compared to m plus q. And if you think about that, it's kind of a rare situation. So this is I would say, I try to sell it now, a very good method that works in most situations. And so it's better than the first the first procedure that I described, and it is under the weakest signal to noise condition that I'm aware of. So that's it.
Maybe a question or two while Martin sets up. So a quick question, do you have any thought about lower bound?
Lower bounds for what?
For estimating the rank of the other parameters for just for any algorithm working.
I prove lower bound if I get the signal condition, right?
Yeah, that's right. Is there a gap between that and like the algorithm? Maybe the question is
No, I mean, when I showed the plot, you got straight lines. Actually, I mean, this was the criterion. So I mean, it was the signal versus the noise essentially.
yeah.
So, yeah.